Hey Chem Kids, Campbell here. In our first video on Chemical Equilibrium, Chapter 17, we're going to talk about reversible reactions and KEQ. So far when we've talked about reactions, we've talked about them as if they just completely go from reactants to products. And some reactions actually do that, like fireworks, right? You light fireworks on fire, you get these beautiful colors, but they don't go back to form the original firework that you bought in the store. Same thing with burning wood, right? You burn wood and it becomes ashes. You can't get them to reform logs. So lots of reactions do proceed completely from reactants to products, but not all do. And those are called reversible reactions. So a reversible reaction is one that goes from products to reactants, and then some of those products will actually go back and reform the original reactants. So I have my forward reaction occurring, where my reactants produce products just like normal, but then the reaction can reverse directions, and now some of my products might break apart and reform those reactants, and those are called reversible reactions. Now, when we symbolize a reversible reaction, we use a double arrow. Now, that double arrow could look like many things. It could look like this, with two arrowheads on it. It could be two separate arrows. It could even look like this down here. So reversible reactions are indicated by a double arrow, but what it tells me is that I can take two NO2 and produce some N2O4, like in this reaction here, but also some of this product, N2O4, can reform NO2, like here. And so I have this reaction going in both directions. I have the forward reaction where reactants form products, and the reverse reaction where products reform the reactants. Pretty cool. So I'm going to show you a little simulation of a reversible reaction. We're going to start off with 200 molecules of A in our chamber, and those molecules are going to collide, right, collision theory, and they're going to form an activated complex where old bonds break and new bonds form, and we get our product B. So here we go, we're forming product B as product A reacts, but you also notice that in a reversible reaction, it's not just that A is going to B. It's not like, when we light fireworks and all of the reactant becomes product. In our simulation here, in a reversible reaction, what's actually happening is A is forming B, and then B, once we get to having enough molecules of B to collide, then B goes back and forms A. In a reversible reaction, we reach this equilibrium stage where the rate at which A goes to B is equal to the rate at which B goes back to A. You'll notice that now we have more particles of B than we have at A. So it's not like they reach the same amount, it's just that the rate at which they're going back and forth becomes the same. So that is a reversible reaction. So let's take a look at this reversible reaction from a concentration standpoint. Concentration is the amount. And in the beginning, if we look at the reaction of N2O4 going to 2NO2, we can see that initially we have all reactant at time 0. We have all reactant N2O4, but as we start to form our product NO2, this concentration starts to go up at the same rate that this goes down. So on my concentration versus time graph, we can see that the amount of reactant decreases as the amount of product increases. Now, eventually we get to this point where those concentrations don't change anymore. So eventually I get to a point where the amount of each stabilizes, and this is called equilibrium. And in fact, this is a dynamic equilibrium. So at a dynamic equilibrium, I get to the point where both reactions are proceeding at the same rate. And so I have some N2O4 producing NO2, but I also have some NO2 producing N2O4, and that occurs at the same rate. So my concentrations no longer change. They've stabilized. We call it a dynamic equilibrium because both reactions are still happening. So I still have N2O4 becoming NO2, and I still have NO2 reforming into N2O4. So these reactions are still happening, even though it looks like nothing's happening because their concentrations aren't changing. And that's why it's dynamic. It's happening, even though it doesn't look like it. Now, if we take a look at the concentration of products and reactants, once we reach equilibrium, they've stabilized. Their levels are the same and they don't change. But they're not usually the same. So here's a reaction where nitrogen gas reacts with hydrogen gas to produce ammonium. That's actually called the Haber process. And in this reaction, I have 3 hydrogens per 1 nitrogen here, producing 2 NH3s. And you can see that on the concentration graph. And you'll notice that at equilibrium, even though their concentrations aren't changing, they are not the same. But the reaction rate at equilibrium is the same. So if we look at it in terms of a rate, instead of looking at it in terms of a concentration, we can see that the forward rate is decreasing while the reverse rate increases till I reach an equilibrium. And at equilibrium, one of the definitions of being at equilibrium is that the forward rate equals the reverse rate. So in summary, a reversible reaction is one in which the reactants form products, but then the products can go back and form reactants. It's symbolized in a reaction equation by a double arrow. It's called a dynamic equilibrium because at equilibrium, even though it looks like nothing's happening because the concentration of products and reactants aren't changing anymore, and the forward and reverse reaction rates are the same, the reactions are actually still occurring. So in that simulation, right, we had the little reactants going to products, and then those products going back to reactants, and they kept going the whole time. So dynamic, it's still happening. It just doesn't look like it anymore. All right, it's time to go to problems. Thanks for watching.